Welcome to Hot Chips 2024. Session 5, AI Processors, Part 3.
Okay, good morning, everyone. Welcome to the session 5, AI Processor Part 3. I'm Yasuishi at Tensor, and I'm the chair of this session. Like the other AI processor sessions, we have 3 very interesting presentations. And as you know, we are accepting the question from Slack. So if you have any question during the presentation, please feel free to post your question on the corresponding Slack channels. And the first presentation in this session is the AMD Versal AI Edge Series Gen 2 for Vision and Automotive from AMD. The presenter is Tomai Knopp and Jeffrey Chu. The Tomai Knopp is a senior director at AMD responsible for IP and SoC development. He is responsible for processing subsystem, NOC, DDR, multimedia, communication IP development, and functional safety. He received his bachelor's degree in electrical engineering from the University of Texas, San Antonio. Jeffrey Chu is a SoC architect at AMD, focusing on SoC architecture and end-to-end application use case. He has many years working in the design and the development of image processing, computer vision, and AI inference-based systems. He received his master's degree in electrical engineering from the University of California, San Diego. Please give a warm welcome to Tomai and Jeff.
Thank you, Yasu. Good morning, everybody. Jeff and I are very excited to be here today to share with you the second generation of the Versal AI Edge family. Before we get started, I'd like to take a moment to thank everybody that contributed to the slides that you'll be seeing today. Today's agenda will cover the challenges and motivations behind the device. We'll go into the silicon features, and then Jeff will wrap things up with vision applications. In today's automotive embedded applications, we tend to see 3 major forms of compute. Pre-processing, where you're taking your external sensor data, you're conditioning and fusing that data in preparation for your second phase of compute. AI inference is where you're analyzing the data, perhaps you're running object recognition. Post-processing is where you're reacting or you're making a decision based on that analysis. It could be generating haptics feedback to the user, steering correction, or even application of the emergency brakes. Today, this is commonly solved by discrete components optimized for each of the processing phases. A multi-chip solution might be what you see on the left, where you have a programmable logic device for your pre-processing, an accelerator for your AI inference, and a high-performance SoC for your post-processing. This being an automotive application, you also have some sort of intelligent safety monitor on the board to ensure that your overall solution stays within the safe operating parameters set by your application. In Gen 2, we can consolidate this into a single device. This not only simplifies the overall solution, but it also addresses the secondary challenges around tight form factor, limited power delivery, challenging thermal conditions, and increased safety and security requirements. Let's take a look at how these map into our current device. For pre-processing, you'll be using our programmable logic, which has been refreshed in Gen 2 to give you 5% Fmax improvement. Thanks. A 5% Fmax improvement and 2% power reduction. We've added support for MIPI C-PHY, and we've hardened a host of video-centric IP, including GPU, ISP, video codecs, and vision processing pipelines. For AI inference, you'll be using our AIE array, which has been refreshed and has architectural enhancements to reduce power, increase performance, and we've adopted several new data types. In embedded automotive applications such as IVI and ADAS, we see a growing and increased demand for compute. And so our post-processing compute, the application and real-time processors have been increased, giving a 10x compute performance uplift from previous generation. Now to feed all this compute, you need to increase the NOC in the DDR backbone, and we now support LPDDR5X and DDR5, giving up to 170 gigabytes of bandwidth. To protect the device, we have state-of-the-art device security, including post-quantum crypto support, and for the first time offering safety channels up to ASIL D. Essentially everything on the device is new or upgraded. Our lead device, the 2VE3858, has 36 billion transistors and around 290 megabit of on-die memory. Before we get into the IP specifics, I wanted to walk through the family plan. There are 6 devices in the family, and I like to organize them as the small, medium, and large devices. If you look at the top row of the table, that will tell you how many AIE tiles are in each device. And you can see that the left 2 devices have 24 tiles, the middle 2 devices have 96, and the rightmost 2 devices have 144 tiles. Our lead device is on the right-hand side of the table. Now within each one of these groupings, you can see that you can include or exclude the vision IP or the additional compute, and that's represented by the small blue rectangles in the table. This gives you a large matrix of devices that you can use to select the appropriate part for your application. Let's talk about the AIE engines. So this is the 2nd generation of our AIE ML architecture and the 3rd generation of AIE in total. You can also find a variant of this architecture in the recently announced XDNA2 in the Ryzen AI 300 series. As a refresher, the architecture is a 2-dimensional array of compute tiles which are connected through high-performance streaming, non-blocking, and programmable interconnect. Each of the tiles can also communicate to its nearest neighbor using cascade interconnects. In Gen 1, we added the memory tile, which allows you to reduce the external DRAM bandwidth requirements. And in this generation, we added the control tile, which reduces the demands on the programmable logic. Now looking at the table on the right, you can see that the throughput will vary depending on the device you select and the data type. Across the top, you'll see 3 devices that represent those small, medium, and large groupings, where the small device with 24 tiles is on the right-hand side, and the large device, or our lead device, is on the left with 144 tiles. Looking at MX6, for example, you can see that the throughput will vary between 61 and 369 teraflops. Let's look at the differences side by side. In Gen 1, we supported 2 data types, int8 and bfloat16. And in Gen 2, we've doubled the number of multipliers for each of those. You double the compute, you have to double the interconnect bandwidth, and I've already talked about the control tile. We've added support for 4 additional data types, FP8, FP16, MX6, and MX9. Now the MX6 and MX9 data types were introduced by Microsoft in a paper that they released in April of 2023, and there are compelling reasons why you might want to consider using these. The paper is linked at the bottom of the slides for your reference. Let's take a closer look at the MX9 and MX6. We'll go bottom up in this slide, starting with accuracy, which was done with drop-in replacement of quantized weights, no retraining, and we use FP16 as our baseline. With MX9, we saw that 80% of the simulations that we did reached 99.9% accuracy when compared to FP16. 100% of the models simulated actually reached greater than 99% accuracy. For MX6, 56% of the models simulated reached greater than 98% accuracy. Both data types give you significant advantages in storage, where MX9 gives you 40% savings over FP16, and MX6 gives you 25% savings over int8. And both data types, MX9 and MX6, give you twice the throughput when compared to FP16 and int8. Now MX6 is more model dependent. However, the advantages that you get in throughput and storage are significant. And if you're able to take advantage of these data types, it will help you meet your price, performance, and power targets. Jeff will cover some more advanced techniques on how to better utilize your AIE array later on in this presentation. Moving to the processing subsystem, we continue to hold the low power domain and the full power domain, where the low power domain can be considered your always on domain. The low power domain contains your real-time processing unit, which is 5 dual-core clusters. These are R52s running at 1 gigahertz. The full power domain has the application processing unit, which is 4 dual-core clusters. These are ARM A78AE cores running at 2.2 gigahertz. The FPD also contains the Mali G78AE GPU, which has 2 slices and 4 shader cores and can operate as a single partition or split partitions. All the slices and CPU cores can be individually power gated, and the entire processing subsystem can operate with no dependency on the programmable logic. Compute uplift from previous generation, as I mentioned, is 10x, or around 230K DMIPS. Moving to embedded security, the PMC, or the Platform Management Controller, continues to be responsible for establishing your hardware root of trust. It's responsible for boot, configuration, test, debug, and platform management, which includes clock, reset, and power management of the entire device. The PMC is CNSA 2.0 compliant, and as mentioned earlier, has post-quantum crypto support for both symmetric and asymmetric secure boot. In addition, all the errors on the device get aggregated into the PMC, and the PMC can replace your external safety monitor. The PMC is also ASIL D fault tolerant. Due to increased demands on the crypto capabilities within the PMC, we decided to add a separate application security unit, which implements a full HSM and is also fully ASIL D compliant. And unique to the ASU, you can extend its crypto capabilities by putting soft ciphers into programmable logic. The memory controller was also updated, now with built-in firewall or memory protection and inline crypto, both AES XTS and AES GCM, for data integrity and confidentiality. As mentioned earlier, we've hardened a host of vision-centric IP. And these IP are optional per the family plan. But in addition to being able to be in or out, depending on the device that you select, they can also be stacked to increase your capabilities. For example, the ISP tile supports up to 5 cameras and up to 1 gigapixel per second throughput. However, in our largest device, you can have 3 tiles, which gives you an aggregate of 15 cameras and 3 gigapixel per second throughput. The VCU has also been upgraded, now supporting H.264 and H.265, and like the ISP, is also a tile that can be stacked. When you stack 2 VCU tiles together, you can support 8KP30, and when used separately, they can support 4KP60. The VCU includes both an encoder and a decoder, which can operate in parallel, and they both support up to 32 streams each. The VPP is a new tile. It's the video processing pipeline, and it supports all the common video processing functions, such as scaling, tone mapping, gamma correction, mirroring, scaling, combining and blending, and so on. It supports 2 parallel streams at 8KP30, and when you use the 2 pipelines together, it can actually support 8KP60. All 3 of these IPs are directly coupled to our on-chip NOC, further reducing the requirements for your programmable logic. And then lastly, functional safety is very important for any application in embedded automotive. And as such, we meet ASIL D systematic requirements nearly across the entire device. And for ASIL B random fault tolerance, you can see that most of the hard blocks support that. That includes the AIE array, the NOC, the DDR, the vision IP, and of course the processing subsystem. But what we're most excited about is the addition of the ASIL D safety channel. This is where the processors are operating in lockstep, and it includes the entire path from the processors through the NOC to the DDR. With that, I'll turn it over to Jeff to talk about advanced concepts around vision applications.
Great, thanks, Tomai. Now that we've gone over some of the key Versal Gen 2 features, let's look at some of the applications that this device was targeted for. As shared earlier, functional safety is built into these devices, along with powerful AI and vision processing, making it suitable for automotive vision applications, such as Subaru's next-gen EyeSight, which we jointly announced earlier this year, would be based on a Versal Gen 2 device. Vehicle cabin applications focus on monitoring occupants. State-of-the-art systems employ AI using 1 or 2 cameras and a combination of infrared and color imaging. Versal Gen 2 excels at the fine control and processing of different sensor patterns required in these type of systems. For outward-facing applications, they utilize a number of high-resolution imagers, with multiple 8-megapixel cameras often being deployed. Multi-camera capture, along with high-throughput video and AI processing is needed, both of which Versal Gen 2 is capable of enabling. In addition to safety, there are a number of user experience applications that rely on AI and video. For instance, with smart assistants, vehicle settings can be tailored based on driver identification in addition to voice commands. Let's walk through an AI and vision-based processing pipeline. For sensor-based systems, the sensor period often determines the processing throughput requirements, along with how hardware and software tasks are allocated within and across different sensor periods. For instance, suppose we have a camera system running at 60 frames per second. That results in a sensor period time of approximately 16 milliseconds. To minimize the end-to-end latency from sensor capture to output decision, the processing within that sensor period must be very efficient, such that we minimize the number of 16 millisecond sensor period stages within that pipeline. In the most ideal case, all the processing would occur in line as the data is being captured onto the device, resulting in a single sensor period of latency. Our customers often have to process multiple sensor data sets. The hardened ISP tiles, along with the programmable logic fabric, can enable custom inline processing, minimizing both system DDR bandwidth along with latency. In addition, conditioning, such as normalization or data format reorganization, can be done inline for downstream AI inference. For AI inference, a single camera output may feed more than one AI model. Outputs from multiple cameras may feed a single shared AI model or multiple different models. We'll see shortly how customers can use Versal Gen 2 to optimize inference for their specific application. Finally, AI model metadata output needs to be post-processed for perception and decision-making. This processing can occur on our processor system CPU cores and in conjunction with our programmable logic fabric. For instance, suppose an AI model produces a large data structure output consisting of potentially detected objects. We've had customers develop custom hardware to filter objects with probability scores that fall below a defined threshold, thus enabling additional CPU cycles for their object tracking application. For sensor pre-processing, our customers love accessing chip IOs via the programmable logic fabric. Customers have implemented in the programmable logic hardware for such tasks as demultiplexing multiple camera streams over a single MIPI interface, in addition to extracting pixel data or embedded data from the pixel data stream. Custom hardware for data path processing, such as stereo vision, fisheye lens correction, or fusing LiDAR data to camera data, can also be implemented by customers for their specific application. Let's now examine some techniques that customers can explore when using Versal Gen 2 for inference. Spatial sharing maximizes the AIE ML array efficiency by concurrently running multiple copies of the same model or multiple different models across the array. As an example, suppose we have two models. Our first model, Model A, might be a free space segmentation model. Free space is the identification of safe drivable space within an image. Our second model, Model B, might be an object classification model, returning detected objects along with their positions within the image. Model A and Model B run concurrently in parallel on the array, accessing system memory for their instructions, weights, and intermediate feature maps, ultimately writing out their results within the frame period. Spatial sharing is advantageous when you have multiple small models and a large AIE array, or when you have a single small model that needs to be run on multiple camera outputs. Alternatively, customers can examine temporal sharing. In temporal sharing, models are run sequentially, where each model is loaded into the array independently, executed until completion before the next model is loaded. As in our previous example, let's assume we have two models. Our first model would be loaded into the array, utilizing all the array resources before running to completion. The next model would then be loaded utilizing the full array as well and running to completion. Temporal sharing has advantages in that it can help spread post-processing tasks over time, potentially hiding latencies in the system. Single model utilizing an array, when compared to that same model running on the array and sharing it with other models, will will complete its inference processing faster as it has all the array and system resources available for itself in that window of time. A post-processing task with a long completion time can then potentially be hidden by enabling its input from inference to arrive earlier. And this would be done by scheduling its corresponding model on the AIE ML array first. In addition to temporal and spatial sharing, customers can explore using data types to optimize their inference. Let's suppose that for model A and model B, we find that the accuracy between using MX6 data types and int8 data types is comparable. As my colleague Tomai shared earlier, the number of tops for MX6 data types in an AIE tile is twice that when compared to int8. What this effectively means is that if we move our models from int8 data types to MX6 data types, we effectively half the number of AIE tiles that are required to run inference. Customers can then examine moving down to a smaller device with less AIE tiles, or remain in an existing device, taking advantage of either spatial or temporal sharing for their specific application needs. Post-processing involves control and decision-making. Often, there will be multiple post-processing applications that will be running concurrently on the system, each requiring its own minimum set of system resources. Additionally, different post-processing tasks may have different safety requirements based on the task at hand. Customers can configure the processing system and assign independent or shared system resources such as CPU clusters, system cache, and paths to DDR based on their specific application. Our camera system will have auto white balance and auto exposure, commonly referred to 2A, running on a per frame basis. In addition, you may have an Ethernet stack running to enable communication between the device and an external component within the vehicle. In this example here, we've assigned these two applications a shared CPU cluster along with system cache partition and path to DDR. AI inference output may feed multiple post-processing tasks, such as perception, localization, and planning. Here, these three applications are assigned a shared set of clusters along with system cache and path to DDR that are independent of the 2A and in-vehicle communication applications. For applications that require or impact human safety, CPU cores can be configured to be run in lockstep for ASIL-D requirements. A full ASIL-D channel can be enabled on the device from CPU clusters to DDR by enabling transaction redundancy that is built into the hardware, along with configuring independent routes through the programmable NOC to independent DDR components. Automated parking follows the pre-processing AI inference and post-processing steps. Automated parking helps end customers by enabling their vehicle to park on its own. In these vision-based applications, multiple surround view camera images are captured and processed to form a single top-down image. This top-down image is then passed through a free space segmentation model where the drivable space is then determined for the vehicle. In addition, object detection would be running to identify any obstacles in the trajectory of the vehicle as it's trying to park itself. Post-processing can then be done on the processor system cores to determine the acceleration as well as the steering angle needed for the vehicle. In addition, post-processing from the GPU on the top-down image can be performed along with the generation of overlays to enable the driver to visualize the current state and progress of the parking application. In summary, Versal Gen 2 aims to simplify the existing multi-chip solutions by integrating hardened compute accelerators along with programmable logic, application and real-time processors, and functional safety into a single device. Versal Gen 2 is a family of all-in-one devices that scales architecturally in the number of accelerators, programmable logic resources, and AI processing throughput. It was designed for automotive and embedded vision applications in mind. Customers can customize not only their software, but hardware for their specific applications, all working in conjunction with the hardened resources. This now concludes our presentation. We'd like to thank you for your time this morning in hearing us share about Versal Gen 2. We'll now take questions.
Thank you very much, Tomai, Jeff. We have two microphones in the hall. If you have question, please line in front of these microphones. And I want to take the question from Slack. Is that ready?
Yeah, thanks for the great talk. This question is from Shrikant Murur, Google. Can you describe how the MX6 and MX9 types are stored in memory? Because neither of them are 8-bit aligned. So can you describe how they are stored in memory?
Take that question. Do you want me to take it? Go ahead. Yeah. So for the MX6 and MX9 data types, you're correct. They're not 8-bit or 16-bit aligned. It is a proprietary internal memory format that'll probably be shared once our documentation is sent out. But it is a tightly packed format.
Okay. Thank you very much. Please go ahead.
Hi, Jeff Smith. Question about the programmable Knopp.
Sorry, please say your name and affiliation before making a question.
Sorry, hi, this is Jeff Smith, actually, and unaffiliated. A question about the programmable Knopp. Does it serve any purpose or functionality besides the ASIL derouting, or are there QoS guarantees or other things that customers can use with some of that functionality?
Yeah, no, obviously it has many more features than the ASIL D requirements. In fact, the ASIL D requirements aren't actually covered in the Knopp itself. We have a block called the TRU within the processing subsystem that does transaction redundancy across the Knopp. As you know, functional safety can be very costly, and if you don't handle it properly, it can have a very bad effect on your PPA if you go around duplicating everything. So the Knopp definitely is responsible for more than just the functional safety. It has out of order processing. It has it's a fully Knopp flip-based, multiple different channels for QoS. Yeah, so it's not for functional safety. It has many more features in addition.
Those features are things that are going to be exposed and exploited by the typical customer, or they're just baseline functionalities that the system needs to operate. Is it end user programmable in a common case sense, I guess, is my question.
Yeah, so that's a good question. So all of our configuration capabilities in the Knopp and in the processing subsystem are controlled by control registers. And so advanced customers may go in and start tweaking things, but most customers will just use the standard configurations coming out of Vivado. And so most of those features will just be automatically handled by our configuration. But again, super users can go in there and tweak things.
Thank you guys very much.
Thank you.
I want to take a question from the other microphone.
I have Xiaoshen Guo from Samsung. I have a question maybe related to what was asked. So for the both AIE ML engine and the post-processing unit, there are some configurabilities. Can you comment on the runtime configurability capability for the two configurations? So one you mentioned for AIE, you mentioned the sharing capability. I would imagine that's runtime configurable, and what's the overhead? The other one you just mentioned is mostly done from registers, but is there any runtime configurability for that post-processing unit?
Want me to take the first question?
Yeah, you can.
Yeah, so regarding your first question on the AI runtime capability, right? I think the intent is that at runtime, you can determine whether it's spatial sharing or temporal sharing. I think they'll probably work towards the future to maybe make it more dynamic when the product is released. Right now, I think the working assumption is that the user can configure it and it's spatial sharing or time sharing, or potentially a combination of both, but it's set before runtime.
Okay, so in terms of runtime configurability, yes, of course you can go and change any of the parameters during runtime if you're careful, right? You can change things at the wrong time. You might have to quiesce the system before you change parameters or you change, firewalls and things like that. But yes, of course you can change all the configuration runtime as you see fit. And then also with the AIE array, we can actually time slice the AIE array, especially when we're running STLs for functional safety purposes. Exact time it takes to switch the context is something that we're still characterizing. So look for that information later.
Do you have a question from Slack?
Yeah, question from Cliff Young, Google. I think your focus has been on inference. Would you recommend building a training system out of your parts, and what might that look like?
Yeah, I think this device, I mean, end customers can choose to do what they want with the device. As we kind of illustrated in the presentation, the main target is primarily for kind of automotive or embedded vision type applications, right? But yeah, in theory, customers can choose to do what they wish with the device.
I want to take last question from this microphone.
Hello, I'm Hyuk-jun from Hyundai Motors. When it comes to automotive, you have to run parallel models like in almost simultaneously. Do you share your idea on like how to really optimize when you run those parallel models on multiple AMD chips?
Yeah, do you want to take? Yeah, so if I understood your question correctly, you're asking, often you have to run multiple models for these automotive applications, right? And so two of the ways we described in the presentation was, it's dependent on your models and specific application, but potentially you can take advantage of spatial sharing if you want to run multiple models. But that assumes the models will fit in the AI ML array. The other option is to practice time sharing, right? Where, let's suppose you have 3 models. Can profile or determine, again, it's model dependent, how quickly inference can complete within the models. So for example, if you do have 3 models, you could time share, completing each model independently. And just based on experience and maybe from what we've observed from customers, that typically helps them with their post-processing tasks in terms of hiding that latency that I kind of described. But you're also welcome to use spatial sharing. It's completely up to the user and your use case.
Thank you.
Thank you very much, Tomai, Jeff. We want to move forward to the next presentation. Thank you. Okay, the second presentation is Onyx is a programmable accelerator for sparse tensor algebra. The presenter is Kalhan Koul. Kalhan Koul is a PhD candidate at Stanford University in the Stanford Accelerator Lab, supervised by the Professor Priyanka Riana. He graduated from the University of Texas at Austin with highest honor in electrical and computer engineering and liberal arts honors. Currently, his research focus is programmable accelerators and agile hardware design. Please give a warm welcome to Kalhan Koul.
Thanks, Yasuo. Hi, everyone. My name is Kalhan Koul, and I'm a PhD student here at Stanford. Today, I'm very excited to present Onyx, a programmable accelerator for sparse tensor algebra. Applications ranging from scientific computing to machine learning can have extremely sparse inputs. For example, matrices in scientific computing can be up to 99.9% sparse. In graph neural networks, matrices that represent graphs tend to be very sparse as well, making graph neural networks sparse. In sparse transformers, the attention portion of the transformer has been shown to be able to be pruned up to 93% sparse. Because data sparsity allows us to potentially skip unnecessary computation, researchers have been building sparse accelerators. For example, at ISSCC and VLSI in the last couple of years, there have been several works that exploit sparsity in machine learning. All of these works are fixed function. These chips are energy and area efficient, but only accelerate a single application, and they don't map well as application evolves. On the other hand, there are prior works that accelerate 2 types of sparse kernels, matrix-matrix and matrix-vector multiplication. These accelerators, however, leave out support for many other sparse tensor algebra expressions that exist in end-to-end applications. For example, high-dimensional tensors are unsupported, so we can't accelerate a tensor times matrix operation. Additionally, multi-input operations are also unsupported, so something like sampled matrix multiplication wouldn't be supported. To accelerate computations like these, we need a highly programmable accelerator. However, most programmable accelerators only focus on dense applications. These programmable accelerators are more energy and area efficient than general purpose computing, but not as good as ASICs. Key advantage of these accelerators is that they can accelerate domains of applications, remain relevant as the application evolves. We present Onyx, a programmable accelerator for any tensor algebra expression that addresses the shortcomings of all the prior work. Utilizing our compiler, we can accelerate the tensor algebra kernels that exist in scientific computing, graph neural networks, transformers, convolutional neural networks, and image processing. Depending on the sparsity of the input data, we can either choose to use our dense accelerator compiler or our sparse accelerator compiler to maximize performance and energy efficiency. We break these end-to-end applications into arbitrary tensor algebra expressions and map them onto data flow graphs. Finally, we map these data flow graphs onto Onyx, our programmable accelerator. This makes Onyx more energy and area efficient than general purpose computing. Onyx supports both dense and sparse application acceleration and can adapt as the algorithm evolves. Here we have the overall Onyx SoC architecture. First, let's take a look at the accelerator subsystem, which contains a global buffer and a coarse-grained reconfigurable array, or CGRA. The CGRA has two types of tiles: processing elements, or PEs, which can be configured to do either in16 or bfloat16 operations, and memory tiles, which contain 4 kilobytes of SRAM each, and specialized memory controllers to support data streaming. To stream both application and configuration data to and from the CGRA fabric, we have the global buffer, which is a 4 megabyte second level memory. Finally, our SoC contains an ARM Cortex M3-based processor subsystem, which manages application execution on the CGRA and off-chip communication. Now that we understand the basic Onyx architecture, the rest of the talk will focus on the hardware we added to build an accelerator that efficiently supports dense and sparse application acceleration. First, Onyx contains composable sparse primitives that allow us to accelerate arbitrary sparse tensor algebra expressions. And second, Onyx has specialized compute and optimized memories for more performant and energy-efficient image processing and machine learning applications versus the prior state-of-the-art CGRA. I'll start by going into detail on our sparse accelerator hardware contribution. As we discussed earlier, prior sparse accelerators have focused on sparsity in specific kernels. To support all of sparse tensor algebra, we need a more general abstraction. Onyx addresses this issue by building on a streaming representation of fiber trees. So what's a fiber tree? The matrix on the left can be represented as a fiber tree. The first level of the tree represents the non-zero rows in the matrix. Here, rows 0, 1, and 3 are not empty. The second level of the tree is the corresponding columns in those rows. For example, in row 3, we have 2 non-zero values in columns 1 and 3. Here, the term reference is a pointer to the next level of the fiber tree. Finally, the leaves of the fiber tree are the non-zero values in the matrix. To perform calculations on our CGRA, we need a format for streaming the levels of a fiber tree between tiles. Coordinates for the level I of the fiber tree are shown in blue for both the fiber tree format and the stream format. Here, the streams for the other levels of the fiber tree are shown. Stop tokens represent end of fibers, and done tokens represent end of levels. And finally, we show the storage format, or how streams can be stored in memory tiles on our array. We partition the memory tile memory into segment and coordinate arrays. Segment pairs denote the length of a fiber, and the coordinates are placed in the coordinate array. Here you can see the 0, 1, and 3 is stored in the coordinate array, and the length of the fiber, which is 3, is designated in the segment array. The reference streams are used to access memories at the next level of the fiber tree. Here, the highlighted 0 in the level I reference stream is pointing to the first segment in the J level. Similarly, the 1 in the J reference stream is pointing to the second segment in the value level. The reference stream is used to perform the random data access that we have in sparse applications. Now that we've gone over the fiber tree abstraction, let's take a look at the hardware we added to our CGRA. To our memory tiles, we add a level writer, level scanner, and level buffer, which allow us to convert between the stream and storage representation of the fiber trees that I just showed. To our PE tiles, we add an intersector, a unioner, a coordinate dropper, a reducer, and a repeater to eliminate unnecessary compute and have the functionality to support all of tensor algebra. First, let's go over the memory tile primitives. The level writer consumes a stream and generates the read and write addresses for the storage format. To do this, it counts the number of coordinates between stop tokens to determine the values that go into the segment array. In this example, we have 3 coordinates, so we should write a 0 and 3 into the segment array. The coordinates themselves are then copied over to the coordinate array. The coordinate and segment address generators generate the SRAM addresses we need to write to. The level buffer arbitrates writes and reads and stores the segment and coordinate arrays. We add cache lines in the level buffer to avoid redundant reads of the same 4-element word in consecutive accesses. The level scanner takes a reference and produces a next level fiber. First, it consumes a reference pointing to a segment pair. In this example, we use the root reference 0. It requests a segment pair from the level buffer to determine the coordinate array length. In this example, we get a 0 and 3 for a length of 3. Then, the level scanner generates the addresses to read the coordinate stream from the level buffer and produces the coordinate stream. So here you can see the 0, 1, and 3 in storage become a stream. Finally, the coordinate FSM also produces the corresponding reference stream for downstream tiles. Utilizing the level writer, level buffer, and level scanner, we can store and process any dimensional tensors. Next, let's take a look at the primitives we add to the PE to eliminate ineffectual compute and support all of tensor algebra. The intersector is used to compare coordinates and keep the equivalent ones. In this example, the streams have coordinates 4 and 8 in common, and so those are forwarded on. Intersectors are used to eliminate calculating any unnecessary values. The union is used to collect all incoming coordinates and remove duplicates. The intersect and union operations are similar and are optimized to share hardware as shown. The intersector can produce empty fibers in a coordinate stream. The coordinate dropper consumes 2 coordinate streams from 2 levels of the fiber tree and removes these empty fibers. Here, the red 2 corresponds to the 2 red stop tokens shown. The reducer is used to sum fibers for reduction in situations like a dot product. In this example, the 6 and 7 are summed to 13, and the 8, 9, and 10 are summed to 27. Finally, the repeater is used to broadcast one stream over another. This is used in situations like a scalar times a vector, where we need a scalar to be broadcast over the non-zero values in the vector. Using these 7 composable primitives, we can support all of sparse tensor algebra. For example, here we show vector-vector element add. First, we find the non-zero coordinates of B and C and only add those values. The unioner produces the resulting coordinates and the adder the final values. Here we have matrix vector multiplication. The repeater broadcasts the vector over the matrix, and the resulting coordinates of B and replicated C are intersected. The multiply and reduce are used to perform the dot product of each row and column pair. With these primitives, we support all of sparse tensor algebra. Our primitives also allow us to support storing and processing high-dimensional tensors and expressions with multiple inputs. For example, we can natively accelerate kernels like tensor times matrix, and multi-input expressions like a sampled matrix multiplication. The key insight here is that for an operation like sampled matrix multiplication, we can take advantage of fusion. Since we know the output matrix will only have values at the locations in the purple sampling matrix, we only need to calculate the necessary indices in the matrix multiplication. And this leads to significant performance improvements. To illustrate this, we use a more sophisticated example from scientific computing, matrices tensors times Cauchy-Rao product, or MTT-KRP. Here we show 2 tensor operations that make up MTT-KRP. An accelerator that could only handle 2 inputs at a time would need to split MTT-KRP into these 2 kernels and perform a context switch between the 2. Here we show the unfused graphs and fused graphs for MTT-KRP, and there are 2 key things to notice. First, we eliminate the intermediate storage for T, which allows us to avoid global buffer transfer time. And second, the highlighted orange intersects in the fuse kernel occur before any of the highlighted red multiplies or reductions. Performing these intersects earlier eliminates any ineffectual compute that may have been performed in kernel 1. This fused implementation of MTTKRP performs up to 6.6 times faster than an unfused implementation. Utilizing the composable primitives that I described earlier, we can accelerate complex expressions in one kernel like MTTKRP on our CGRA. Now, let's take a look at our dense accelerator improvements. The first challenge we approached was improving compute density. In the prior work, Amber, the ALU only consumed 37.8% of the PE tile area. Additionally, the PE utilization on our array was low because to further unroll our applications, we needed significantly more PEs. To improve our compute density, we utilized an automated processing element exploration tool called Apex. With Apex, we first take the compute graphs of all of our applications and mine the frequent subgraphs. Here you can see we took the image processing applications and convolutional layers and selected the frequent subgraphs across applications. Next, we order the subgraphs by a number of non-overlapping occurrences. You can see in this example, a number is assigned to each subgraph, and they are ordered from left to right in descending order. We select the green subgraphs to merge and ignore the red ones as they either have a high area overhead or don't occur often enough in the application. Finally, the subgraphs are merged into a PE. Here is the baseline PE before subgraph merging. The baseline PE had 2 inputs and supported a standard instruction set. Here you can see the PE after the subgraphs are merged. Let's step through what was added. First, a connection box and input is added to the PE. Then, several muxes are added to the PE to allow us to do 3 input operations without duplicating operation circuits. The one operation circuit we do need to duplicate is the adder so that we can perform a 3-input add. With all of these components, we can now perform a multiply add, a 3-input add, a min-max, and a multiply shift in a single PE. The increased compute allows us to further parallelize our applications, and we can reduce runtime by up to 50% for Harris corner detection and ResNet convolutional layers. Our second challenge was to improve the ratio of controller logic to SRAM in our memory tile. In Amber, the SRAMs accounted for 32.1% of our memory tile area. To understand our optimization, let's first understand the architecture of our baseline memory tile. We utilize a wide fetch SRAM with 2 input and 2 output ports by aggregating inputs from the CGRA with serial in parallel out buffers and separating SRAM words into CGRA words with parallel in serial out buffers. Then we add address generators, which are used to produce the affine access patterns that we have in dense applications. Our first optimization is simplifying the write controllers by reusing the addresses generated by the read address generator and adding a delay block for read, modify, write operations. Our second optimization is reducing the depth of our serial in parallel out FIFO to match our applications. And our third optimization is pruning our counter and configuration registers down to just what is needed for our domain of our application domain. These optimizations allow us to reduce the total area of our memory tile by 24%. Now that we've gone over all of our hardware contributions, here's the Onyx chip. Onyx was taped out in GlobalFoundries 12 nanometers and achieves a peak 571 gigaops and a peak 756 gigaops per watt. To run applications, we've built an end-to-end application flow for dense and sparse applications. Here we show the sparse application flow. We start with the sparse tensor algebra expression. The sparse tensor algebra expression is fed into the custard compiler, which converts the application into a graph of generic sparse primitives called a sparse abstract machine. Next, the mapper converts the generic primitives onto actual PE and memory tiles on our array. Finally, we place and route the application and generate the bit stream for the CGRA. The dense application compiler is very similar, but instead Halide is used as the application language. To evaluate application performance and efficiency of dense applications on Onyx, we took a set of representative benchmark image processing, computer vision, and machine learning applications written in Halide and compared against a set of CPUs, GPUs, an FPGA, and a state-of-the-art CGRA. To evaluate application performance and efficiency of sparse applications, we measure several sparse tensor algebra kernels and compared them against CPUs with sparse libraries. For 2D tensors, we use the Sweet Sparse dataset, which has matrices from a variety of scientific and engineering domains. For 3D tensors, we randomly generate our own tensors. Here, we have the energy delay product comparison between Onyx and other platforms. As you can see from this graph, Onyx significantly outperforms these platforms in terms of EDP. For ResNet, we've compared a few of the representative layers against Amber to show performance and energy improvements. And here we have the energy delay product comparison between Onyx and CPUs with different sparse libraries. As you can see from the graph, Onyx significantly outperforms these libraries on an EDP basis for this set of applications. In conclusion, Onyx is a reconfigurable accelerator that targets both sparse and dense data. Onyx utilizes composable primitives to support any arbitrary sparse tensor algebra kernel with support for complex expressions with multiple dimensions and multiple inputs. Onyx improves upon prior work's dense acceleration with increased compute density and more efficient memories. We've also built an end-to-end compiler capable of mapping applications written in Custard and Halide onto our CGRA. We achieve up to 565 times better EDP over CPUs for sparse applications and 85% lower EDP versus the Amber CGRA on dense applications. With Onyx, we're able to accelerate domains of applications and can continue to support applications as they evolve. Last but not least, I'd like to thank our funders for making this work possible and our team at Stanford for building this chip with me. Thank you all, and I'd be happy to answer any questions.
Thank you very much, Kalhan. As usual, so please line up in front of microphones, but I want to take the question from Slack first, sorry.
Yeah, this question is from Shashank Nemavarkar, Condor Computing. What is the overhead for streaming data to be converted to the storage format at runtime? And where does this format converter reside and execute?
Yeah, so we place the data in a compressed format in our global buffer, and we've offloaded that to the compiler. So right now we haven't analyzed like that conversion, but in future versions of the chip, we're adding primitives that convert between sparse and dense storages and streams on the fly. So that will be done very efficiently there.
Okay, please go ahead for.
Hello, is this live? Mark Hill, University of Wisconsin. I have a three-part question dealing with the overhead of the addresses. So how large are the addresses or pointers? What fraction of your SRAM is taken up by the pointers versus the data? And how will this change as the actual data formats get smaller and finer?
Yeah, so for this programmable accelerator, we focused on the N16 and bfloat16 format so that we could, eventually add any application. So we use N16 for the pointers. So in this compressed format, if the data is very sparse, then the ratio of metadata to data is higher. If it's not so sparse, then it'll be lower. Does that answer your question?
50% addresses then? The SRAM?
No. So the way the fiber tree works is the segments take up significantly less area or less space in the memory. Yeah.
Please go ahead.
Xiaoxuan Guo from Samsung. I have a question about the fusion optimization you described. So you mentioned the intersection step is moved ahead to reduce the overhead, but from earlier slides, it also occurred to me that the intersection is placed inside the PE. Is that the case? If so, then don't you need to go through the entire PE to do the intersection step first? So that's my first question, and you can first answer that. I have a second question too.
Sure, that's a great question. So all the composable primitives I described either exist in a memory tile or a PE tile. And so then given our kernel, which has some connected graph of these primitives, we then map it onto our CGRA. So kind of similar to what Samba Nova was showing yesterday. Then we statically connect the PEs and memory tiles and run the application. So like, for example, if our application does an intersect and then a reduce, we'll be using one PE tile for an intersect, and then it'll be connected to another PE tile, and we'll do the reduction in that other PE tile.
I see. So you don't need to go through the entire.
No.
Okay, thank you. My second question is, I see that you've compared your result with other FPGA configurable implementation or CPU implementation of Sparse, but have you compared with a non-configurable Sparse accelerator, Sparse tensor or Sparse matrix accelerator?
Yeah, so there are several matrix vector accelerators that are a lot of FPGA works in research. We haven't had the time to compare directly with them, but from a high-level standpoint, right, we offer the composability to represent all of sparse tensor algebra. So we should compare with those dedicated accelerators, and we will in the future.
Thank you.
I want to take the question from Slack.
Yeah, so this question is from Cliff Young, Google. My standard question for any architecture that targets sparse workloads is, where is the global associative structure? A lot of the time, such proposals end up with some giant n-port parallel store buffer or crossbar, where all the complexity lives. So in your design, where is that?
So I think I'm not sure if I fully get the question, but the complexity is, since it's programmable, every single tile has an intersect or a reducer. The memory tiles all have level writers, level buffers, level scanners, and they're not going to all be used at the same time. So we clock gate those blocks, but that means that we have some silicon that's not being used while the application's running. And in future works, I've worked on increasing our array utilization, and so future chips will have even better utilization than Onyx.
Thank you. Please go ahead from this microphone.
Yeah, Luca Benini at Zurich. So maybe one thoughts about the future. I know that it's not on your chip, but what will happen when you start looking into global memory access? All these fiber blocks are variable length and very irregular in size. So how can you ensure that you will not lose all the efficiency when, instead of accessing SRAM, you will have HBM, for example, which benefits from very large blocks?
Yeah, so that's a great question, and that's something that actually compiler students in our lab are looking at right now. We're looking at strategies to pack the data so that it's even. So when we stream in tiles, so if you think about a matrix multiplication, we break it down to a tiled matrix multiplication. And so what we can do is we can stream all of those tiles into the array at the same time, and we can pack them such that they fit in nice sets of numbers, so like powers of 2, that sort of thing.
Please go ahead.
So again, question from Cliff Young. Can you comment on the level of sparsity that your design targets? HPC sparsity is in the 1 non-zero in 10 to the power or 10 to the power of 4 or 10 to the power of 5 zeros, while neural networks are more like 10 to 50% non-zero. So can you comment on the level of sparsity?
Yeah, that's a great question. So on this accelerator, we can take a matrix multiplication, either map it in a dense way or a sparse way, and the crossover point for us is around 97%. And for most machine learning applications, that's not great. For the sweet sparse data set, scientific computing, everything that's above 99.9% sparsity, it does very well. We've worked on a bunch of optimizations to Onyx, which we're going to tape out again. And then I've shifted the point from 95 to 97% to like 88% for sparse matrix multiplication, which enables things like the attention portion of transformers, which people have shown have been pruned to like 93%. Yeah, great question.
You have some more questions? Okay. Can I ask one question then? When we think about, for example, large language model, the memory footprint is going to be significantly big, and people often want to use multiple chips to calculate the same workload. When you want to apply this accelerator to such a kind of problem, what kind of network you are thinking about?
Yeah, so I think for really large language models, like our academic chip is a bit too small. But the way we've designed it is we can stamp it out over and over again, right? So we have extremely, our programmable accelerator is very homogeneous. You can copy paste it and grow it given your chip area. And then in terms of moving data from chip to chip, I've talked to Luca Benini's question was asking about that, and that's something our compiler team is looking at, how to pack the data so we can efficiently transfer it.
Yep. Thank you very much. Yeah. Thank you very much, Kalhan. I would like to move on to the last presentation in this AI processor session. That is the next generation MTIA, Meta's recommendation inference accelerator from Meta. The presenter is Mahesh Maddury and Pankaj Kansal. The Mahesh Maddury is the ML architecture lead at Meta. Prior to his current role, he has held senior technical leadership roles at the early stage startups and the established companies like Cisco, Brocade, and Intel, where he has delivered multiple high-performance ASICs. Mahesh holds a master's degree in electrical engineering from the University of Colorado, Boulder. The Pankaj Kansal is a seasoned ASIC design engineer at Meta, where he leads the design of AI/ML accelerator, as well as RDMA-capable NIC. With a robust background, he has previously contributed to ASIC and the SoC development at Broadcom and Marvell. The Pankaj holds a master's degree from IIT Chennai. Please give a warm welcome to Mahesh and Pankaj.
Thank you, Yashua. Thank you. And good morning, everyone. It's great to be here. In this segment, Pankaj and I will talk about the next-gen MTIA, which is Meta's training and inference accelerator. MTIA has been a huge cross-functional effort, and we'd like to acknowledge everybody who's contributed to it. And of course, our apologies if by mistake we forgot to list anyone. Okay, I'd like to start this off by talking a little bit about the models that we're using and also some of the development goals that we set up for this product. So DLRMs, or deep learning recommendation models, are crucial to Meta's business, and they're a core component of the models that we use for our family of apps: Facebook, Instagram, WhatsApp, etc. When we look at model trends over the last few years, we see significant growth in a few areas. First, the model size, which is the memory footprint of the embeddings stored on the device. That's the yellow line on that plot you're seeing. Second is the model size as a whole, including all tensors that we use. That's the blue line. And lastly, model complexity, the pink line, which is the number of computations we need to do per sample. GenAI, LLMs, these are becoming extremely popular. They are popular. They'll continue to be more popular. And with those coming into other areas, we expect that this trend will continue moving forward. We deploy GPUs in our data center, and we've seen that there can be some challenges. Our workloads have very specific aspects, and due to these requirements, the workload effective performance that we see is not always the same as the peak performance that the device can deliver. Deploying large-scale clusters of these devices can be resource intensive, both from cost and power perspectives. And lastly, we just talked about GenAI. They will become more popular moving forward. This tends to create a supply challenge, which can be a constraint issue or capacity issue at our end. So when we went about designing the next gen of our product, we set up a few development goals. We wanted to improve the performance per total cost of ownership and the performance per watt compared to the previous generation. Total cost of ownership here is at the rack level, not just at the silicon level, and it includes both CapEx and OpEx. We want to deliver high compute efficiency for a variety of models that we use at Meta, And we also wanted to deliver good developer efficiency so that we could reach these large-scale deployments relatively quickly. So I want to spend a little bit of time talking about the features at a high level, and then through the rest of this talk, we are going to be deep diving into many of these areas. So if we just start with gen-over-gen performance, we improved the matrix multiplication performance by 3.5x compared to the previous version. We also introduced support for sparsity, which, if we have the right use case, can give us up to a 2x uplift. We've added some advanced features like ANS weight compression, which can be used for optimizing the tensor movement from memory to the processing elements and improve the performance of that step. We've also focused on the balance between the compute, memory, and data movement capabilities so that we can deliver high efficiency for our workloads. On several of them, we are seeing greater than 80% compute efficiency. Dynamic quantization is an advanced feature that we've added specifically for matrix multiplication. It allows us to deliver very close to FP32 accuracy at int8 performance. When we look at work or job dispatches on the device, and I'm only focusing on the device here, I'm not including the host to the device component. If we just talk about work dispatch on the device, we have improved the new job placement as well as the completed job placement times. And we believe that this can be useful in providing a better PyTorch eager mode experience. And lastly, we have introduced a variety of optimizations for TBE. TBE, or table batched embedding, is an embedding operation that is at the core of deep personalization. It's very important to our business also. We have a lot of system-level improvements, and we've also added specific features like index-aligned DMA. And through these, we are expecting to see close to 2 to 3x improvement on this operator. At this point, I'd like to hand it over to Pankaj to cover some of the details.
Thanks, Mahesh. So as Mahesh already laid out the foundation for the motivation and the goals we have for the next generation MTIA. So in the next few slides, we'll go over the architecture details of the accelerator, mainly focusing on the improvements we made in this generation. This is the top level view of the die that was taped out in TSMC 5 nanometer, and it is designed to run at 1.35 gigahertz of the clock speed. In terms of the gate count, we are looking around like 2.35 billion gates and 103 million flops. The dimension of the chip is like 25.6 by 16.4 mm. The total area is 421 square mm. The die is packaged on the 50 mm by 40 mm package size. The total thermal device power is around 90 watts, depending on the technology, clock speed, and the workloads we are running. The total jump stops we can achieve is like 354 for the int8 and 177 for the FP16. With the sparsity, we think we can achieve twice the performance. The device is designed to support memory capacity up to 128 gigabyte using the LPDDR5 6400, achieving 204.8 gigabytes per second of the aggregated bandwidth. This is the high-level view of the architecture. As you can see, the device, the compute core is built using 8x8 processing element grid, which is supported by the memory subsystem. Memory subsystem is distributed among all 4 sides of the grid. Memory subsystem we are using the memory spray approach to access the memory subsystem. P grids connected, P is in a grid connected to each other and also the memory subsystem via a custom interconnect called Knopp. Memory system supports 64 megabyte of the SRAM, on-chip SRAM on each side. So that brings you to total 256 megabyte of on-chip SRAM, providing 2.7 terabytes of aggregated bandwidth. The on-chip memory is can be connected to LPDDR5 memory using the 16 channel distributed on 4 sides, providing up to 128 gigabytes of total capacity and 204 gigabytes of aggregated bandwidth. Host interface and then the control subsystem, as shown in this figure. They are the main entry point to the SoC. And they are responsible for preparing the job and placing the job in the PE grid, which is one of the function among all other functions. So now we'll little bit talk about the host interface and control CPU subsystem. So host interface and control CPU subsystem, they coordinate together to prepare the jobs and schedule the jobs in the PE grid. They are also responsible for coalescing the completions from the compute grid and firing the completion backs to the host. Host interface is supported by 8-lane Gen 5, providing up to 32 gigabytes per second of total aggregated bandwidth. It is also supported by 4 megabyte of the PCI descriptor SRAM for the faster descriptor fetch to improve the PCI DMA performance. Control CPU subsystem is supported by quad-core scalar RISC-V with 8 megabyte of the L2 cache. It also supported by the 4 megabyte of the context SRAM to support the job preparation and scheduling among the Ps in the compute grid. As we talked earlier, all the subsystem, including the host subsystem, CPU subsystem, P grid, and the memory system, they are all connected by a custom optimized interconnect called Knopp. Fundamentally, the Knopp is divided into two functionality, the data Knopp and then the config Knopp. Data Knopp is the high bandwidth Knopp that carries the tensor data among all the subsystems, and it can provide up to 2.76 terabytes per second aggregated bandwidth, which is 3.4x compared to the last generation we have. Data Knopp also supports various QoS features among all the traffic classes, and it provides non-blocking forwarding behavior among those traffic classes. Data Knopp supports multicast read from the PEs, improving the memory as well as the Knopp aggregated bandwidth. On the other hand, config Knopp is a low bandwidth Knopp that carries the configuration, debug, messages, interrupts among all the subsystems in the SoC. Even though it's a low bandwidth Knopp, but it also supports various QoS features among the different types of traffic we go through this Knopp. And also those QoS features provides non-blocking behavior among different traffic classes. It also supports subsystem level broadcast for a faster initialization, and also selective multicast for faster workload dispatch to the PEs.
Okay, let's talk a little bit about the processing elements which are there on this device. So each PE consists of 2 RISC-V cores, 1 scalar core and 1 core with vector extensions. Both of them offer support for custom instructions. We define and develop the ISA for those custom instructions and are backed by a command processor that's responsible for coordinating between the various functional elements. DPE, which is the dot product engine, is the key matrix multiplier. It supports a variety of numeric formats as well as sparsity. The reduction engine, or RE, is responsible for partial product summation as well as the advanced features like dynamic quantization. MLU is responsible for data movement, reshape, alignment, and those sorts of operations. And nonlinear functions, such as activations and exponents, are covered by the streaming engine, or SE. In addition to these, we have a couple more. SDMA supports weight compression, and WQE is the engine that's used to dispatch work into the PE. Pankaj will cover the details of these in the coming slides. We mentioned earlier in the overview, we offer 177 teraflops per second of bfloat 16 matrix multiplication performance. That's a 3.5x improvement from the previous generation. It translates to about 2.77 teraflops per PE, again at bfloat 16. One of the things we've done in this generation is we have improved the performance of a lot of the companion units. So for example, the MLU, the RE, the SE, and so on. We have beefed them up to be more balanced and match better with the DPE engine. And this is actually really important and a big part of delivering high compute utilization. The PE's memory subsystem has also been improved. We now have 384 kilobytes of local SRAM. This allows us to handle larger tensors easily and thereby support more complex workloads. And the interconnect between the PE and the custom NOC that Pankaj just talked about, that's also been beefed up. This is again very critical to delivering high compute efficiency because we don't want the compute elements to be starved. We want to be able to move data in and out as quickly as possible. Let's talk a little bit about dynamic quantization. So this is an advanced feature that we have introduced in NextGen. It's currently work in progress. We've not yet landed it in our data centers. But at its heart, this is hardware-based tensor quantization. So while the compute kernel is executing on the device, we have the ability to collect the tensor min-max information. We can then use this information to have more precise scaling and quantization of the outputs. And the expectation is that this will allow us to get very close to FP32 accuracy, so less than 0.05% of any errors. But we are able to do this at int8 performance. So we are able to get the real throughput to it.
So Mahesh talked about a lot of improvements in the architecture. And so now from next few slides, we'll focus on the improvements we made for the data movement, tensor data movement in the accelerator. We'll start with the eager mode. So first question we need to answer, what is eager mode? Eager mode is the default, PyTorch default computation mode that execute operators as they are being called. It creates a separate kernel for each operation. And that involves loading the data from the memory, executing the operation, and writing the result back to the memory. So this basically leads to the very interactive programming styles as you can see the result as the operations are being executed. What is this required in the accelerator to support it? It requires we need to launch the jobs and complete the jobs sooner, as soon as they are being called. So from the accelerator point of view, we had the goal, the jobs can be prepared and placed in the compute grid while the compute grid is busy executing the current workload. So to achieve that, we added two features in the SoC. The first one is we added the multicast write group supports that allows control core processor to push the work queue descriptors in the PEs while the PEs are executing the current workload. And this is a broadcast write, so they only do in the single write. The another feature we added in the PEs, we added the work queue engine. Basically, that does the DMA. DMA, the descriptor from the shared SRAM to the local SRAM in the PE. With adding both this feature, we could improve the job time by 80% compared to the previous generation. The second improvement we did is the hardware decompression. This is to improve the embedding fetch improve the fetch time of the embeddings from the host memory. In the previous generation, we observed the large embeddings fetch from the host memory to the device memory contributes the SLS performance drop. So to alleviate that, we added the runtime hardware compression engine inside the accelerator, and that is supported by the RFC 1952 standard encapsulating RFC 1951. It also supports static and dynamic Hoffman coded blocks. They are four separate, the decompression engine is built using the 4 cores. They run in parallel, providing 25 gigabytes per second decompression rate. The third data movement enhancement we did is the PE weight compression. That allows us to compress the weights and place into the device memory, improving the on-chip memory footprint as well as the NOC bandwidth. So it uses the lossless asymmetric numerical system called ANS algorithm that works on the 32 by 32 byte block of data, providing 32 byte per cycle decompression rate. We achieved close to 50% of the compression ratio using this feature. The fourth one and the last one is the improvement for the table batch embedding performance improvement. I think Mahesh little bit briefed about it. So what is TB? TB combines the separate embedding batch ops into a single table. And to improve the TB performance, we introduce index-aligned DMA to prefetch the indexes and place into the local SRAM of the PE. We also added one more feature like hardware decompression we already talked about in the previous slide. With both these optimization and other optimization, we think we can improve the performance of the TB 2 to 3 times compared to the previous generation. So far, we have discussed about the motivation goals and then the architecture improvement we have done in this accelerator. So now, in the couple of slides, we'll talk about the system design. This is the picture of the module. So we have upgraded the module from dual M.2 to CAM full height, full length form factor that can accommodate 2 MTIA in one board. The board TDP is 220 watt. It supports 64 gigabytes per second Gen 5 PCI interface to support both MTIAs. It also supports 256 gigabyte of the LPDDR5, again, to support both MTIAs. This is the top level view of the system topology we have in the data center. So as you can see from the figure, there are 12 modules per chassis, and there are 3 chassis per rack. So there are total 72 MTIAs per rack. And we also have optional memory expansion for future larger, to basically execute the larger workloads in future. This was deployed in data center since first half of 2024.
All right, so we'd like to conclude this talk by providing some of the performance metrics that we've actually collected from the fleet, having deployed this device into our data center. So like Pankaj mentioned, real deployment has only started this year, so we're still, bringing it up to speed inside our data center. So for evaluating this, we compared the next-gen MTIA against a baseline accelerator using a set of models, a set of recommendation models, and we used both low complexity and high complexity models. Low complexity models have about 7 million flops per sample, while high complexity models have 680 million flops per sample. So there's about a 100x difference between those two. The baseline that we chose as the reference is the most optimal in terms of efficiency that we have currently deployed in our data centers. So over the last several months, we have been iteratively optimizing our models to improve the performance. These improvements could be kernel performance tuning. They could be graph optimizations, such as more fusion or op removal and so on. They could also be tuning some of the host side behaviors so that the movement from host to the device also improves. When we look at the overall performance at the rack level, when we look at the peak performance at the rack level of the next-gen MTIA and the baseline system, they are very comparable. The metric that we're using is the workload performance of next-gen MTIA relative to the baseline. So as you can see from this, as the software stack matures, we take less time to optimize a new model. An example is LC1 and LC2. Both are low complexity models, so same in that 7 million flops per sample range. But LC1 took much less time to reach the same performance level as did LC2. So obviously, there's a lot of learnings that we're able to take from one model iteration to the next, which is great for developer efficiency. So if you look overall across the set of models that we have evaluated, the next-gen MTIA is able to either meet or exceed the performance of the baseline system. Low complexity models show very quick, immediate out-of-the-box value. The smaller embeddings that they have make it much easier to have higher locality on the on-chip SRAMs. High complexity models, they have much larger tensors. They need more optimizations, And they need careful optimization, whether it's related to gem tiling or whether it is related to fusion and so on, to keep the working set in the on-chip SRAM. Moving forward, we do expect that MTIA or next-gen MTIA can provide a rack replacement ratio greater than 1. So from a production deployment perspective, that's what we would want. Of course, this is dependent on it meeting the cost and power budget. But if you look at the perf per watt metric that this chart shows, in general, we are meeting it or we are able to exceed the baseline system. The only exception is the high complexity 2 model. This is actually actively in work in progress right now. And we're looking at further items like storing activations in on-chip SRAM to improve the performance. High complexity models are difficult. We do expect to do more work on them. But we do believe that over time, we will be able to surpass the baseline system on them also. With that, I'd like to open it up for Q&A. Thank you.
Thank you.
Thank you very much, Mahesh, Pankaj. So we want to take the question. As usual, please line up in front of the 2 microphones. And I want to take the question from Slack first.
Yeah, a couple of questions on weight compression. So this question is from Abhinav Golas, Apple. Can you comment if the weight compression is lossless or lossy? And if it's lossy, can you discuss the quality loss with quantized representation like int8 or int4 or FP4?
Sure, I can take that. The compression is actually lossless.
Okay. And a follow-up, can you comment about the weight compression ratio?
Yes. For integer numeric formats, we expect to see close to 40 to 50%. For floating point, it's a little bit lower, but even there, we have options where we can split the mantissa and exponent and try to do them separately. I do want to couch all of this, and I just want to reiterate what I said earlier. We have analysis which shows all of this, but we have not actually landed it in our data center. This is currently underway. But we do expect to see value from it.
Thank you.
Okay, I want to take the question from this microphone.
Hi, this is Nathan Brookwood in Site 64. Can you explain why you focused on FP16 as opposed to FP8? And do you support any other formats?
That's a good question. So FP16 is what we're currently using for serving workloads in our data center. So we did pick that. We do support int8, we support int4, and we support bfloat 16 in this generation of the product. Moving forward, of course, we'll evaluate what are the other popular numeric formats and see what makes sense for us and add support for that.
Okay, thank you.
Thank you.
I want to take the question from this microphone.
I was wondering if you could comment a bit on why did you guys choose to use deflate, which is the format that compression format for what I understood was for embedding indices, right? So it is my understanding that first of all it's super old, it's 30 years old, and then one part of it there is Huffman coding, and then you guys already have ANS, and then Huffman coding is the absolute version, right? Rather than ANS, less efficient. So and then we have LZ parts. Z77, which makes sense for the text, but then for embedding indices, there is no repetitions, there is no patterns, because each individual index is unique. So I was wondering if you guys, how did you guys made this decision to use the deflate, and did you guys try other formats? And what are your plans to investigate regarding the compression of the indexes looking forward?
So I think there are a couple of parameters there to select the deflate mode, right? So as you mentioned, so for the ANS, actually we used for the weight compression, and that is we replicated in all the P's inside the compute grid. However, the decompression is only done for the embeddings, for the hardware decompression using the RFC 1952. And that one, because of the design and area constraints and the availability of the design, we picked. And also we ran a few performance models using both algorithms, and then we basically went with this Huffman coding.
Thank you.
Go ahead.
Can you describe what's the baseline system that you're comparing to?
So I'm going to give an answer, and it's going to be extremely unsatisfying. I can't really disclose the baseline system.
Please go ahead from this microphone.
Hey, this is Patrick from STH. Quick question. On your system diagram, you have shared memory between the host CPUs, PCIe switches, all that kind of stuff. What is that being used for, and what is it? Is it like CXL memory, or what is that?
Is that the on-chip memory you're talking about, or off package?
There was
I think he's talking about that yellow box on the system topology where we had the additional memory between the two.
Okay. I'm not sure, because that is the option we left it for the future expansions.
Okay.
So that is not something, maybe at least I am not aware of.
So that's right. So it is an optional memory expansion. We have not put it in our current racks, but it is available if we want to do it. And to answer your question, yeah, it's PCIe or CXL.
Awesome, thank you.
I want to take one last question from Slack, and then I want to wrap up.
Yeah, so this question is on sparsity from Abhinav Golas, Apple. Can you describe the sparsity structure of applications where MTIA delivers 2x throughput?
That's an excellent question. So sparsity is not yet deployed in our data centers. There are, of course, there is literature where, things like 2-4 sparsity and others, where if you run the correct sparsified step in training, then when you are serving that same model, you can achieve up to 2x. I don't think we are claiming that we will get 2x. When we deploy it and when we run real models on it is when we will know where we will actually land. So the analysis shows that, yes, under certain circumstances, we can get close to 2x, but we'll have to see what the reality is for our specific workloads once we deploy it.
Okay. Thank you very much, Mahesh, Pankaj.
Thank you.
And now we'll wrap up this session. Thank you to all our speakers for their presentation.